Good morning. This is Ms. Billerbeck, and we're going to talk about 8.1 linear functions. So a variable y is a function of another variable x if for each x there is only one y. So what that means is if I take a vertical line and each one of these is my y, these is my x's, I should only cross that line once. Okay, when I do that and I only have one intersection with my vertical line, I have passed the vertical line test. So that means that it is a function because for every one of these x's, that means there is only one y. So that's why the vertical line test is so awesome. Okay, so what does that mean? It means if I plug a 4 into my little function machine, and I put it into this function, I have 2 times 4, which is 8, and subtract 1, the output is a 7. So I have an input right here, which is called x, and an output, which is called y. So it's kind of like one of those vending machines. So when you put money into a vending machine and you push the button for like those really hot red Cheetos that are really super messy, and then it comes out and you have like some healthy Nutri-Grain bar, okay? And then you're really bummed, baby, because you put your money into the machine expecting one result. Okay, so you had an input expecting one output, and then you got a completely different output you weren't expecting. So that machine is not functional. Okay, that's how you should think of it. Okay, so when you put an input into a function, it will only have the expected output. Okay, one expected output. Okay, so if a function can be represented by a table, well, a function can be represented by a table. So if I set up x and y, this is considered a table. So if I put in my inputs here for my x's, then I would get these outputs for my y's. So x is in complete control of the y. Okay, it's the input. And y just does whatever the x is telling it to do, basically. So the ordered pairs. So I would represent x first, then y. So 2 comma, -2 comma, -4, and -1 comma 1, and 0 comma 6, and 1 comma 11, and 2 comma 16. So it goes on like that. And we can also represent a function with a graph. So if I just graphed a few of these, we know that you only need 2 points to make a line. So I'm doing a little overkill here with 3 points. Okay, so I have 0, 6, which happens to be called a y-intercept. So this is kind of cool. Y-intercept. Okay, so that's kind of cool where the y, it's like a football player getting an interception. It's intercepting that line right there on the y-axis. And then I have just my -1, 1 is plotted here and -2, 4 here. And look at this. I get my little vertical line test going and it passes. Very cool. So if I was to make an equation out of this, I would start with the y-intercept right here, that's 6, because that's how it starts. And then I would see that, if I counted this out, it rises from 1 to 6 by 5 and then moves over 1 to be right there. So it would be a rise of 5 run of 1, which 5 over 1 is just 5. So this is called the slope, the rise and run. But we'll go into that a little more. So functions can be written in tables coordinates, graphed, or in an equation. So let's practice that. So the initial depth of water in a tub is 24 centimeters. Okay, the water level decreases by 4 centimeters per minute. Let Y be the depth of the water after X minutes. Okay, so at time 0, the tub, which was the initial depth, was at 24. So we're going to put a little point right here at 24. Okay, and it says the water level decreases by 4 centimeters per minute. So if this is 2 minutes, that means I've decreased by 8 because 2 times 4 is 8, or 4 plus 4 is 8. So if we decrease this by 8, I'm at 16. And 4 times 4 is 16. So if I decrease this by 16, I get 8. And if I decrease it, 4 times 6 is 24. So 24 minus 24 is 0. Okay, so if I plot these points, at 2 minutes I had 16. At 4 minutes I had 8. And at 6 minutes I had no water left. And I could plot this, and I have a nice straight line showing how the water is slowly leaking out. Okay, so, and it passes that vertical line test that I've been talking about. So if we are going to write an equation, we write it in this form: y equals mx plus b. So m is how it changes, the slope. Well, it's decreasing by 4. So instead of putting a positive 4, we're going to put a negative 4 because it's decreasing. Okay, and then it started at 24. So b is where it starts. So let's try this out. So at 0, negative 4 times 0 is 0, so that's 24. At 1, negative 4 times 1 plus 24 is 20. At 2, negative 4 times 2 is negative 8. That's 16. That's what we have. Let's try 4. So negative 4 times 4 is 16, which is negative 16 plus 24 is 8. And at time 6, negative 4 times 6 is negative 24 plus 24 is 0. So that's how you make an equation. Okay, and this is called linear modeling. When we take a real life equation, a real life situation like a bathtub leaking or draining, and we put it into a graph, or we put it into a table format, or find an equation to predict the future. That's linear modeling, using linear equations. Linear means our x variable only has an exponent of 1, which we don't write a 1, so there's never a 1 right there. So a linear function written in slope-intercept form with m and b as constants. Okay, so we just talked about that. So y equals mx plus b. Well, m is the slope, the rise of run, or the rate of change. There's a lot of things it's called, or how it changes. B is where it starts at when x equals 0, the initial value. It's also called the y-intercept, where it hits the y-axis at 0, b. Okay, so there's a lot of things that this equation, these two variables can be called, but basically that's the slope and that's the y-intercept, and this, so that's why it's called a slope-intercept formula. All right, so our table shows the distance y kilometers traveled while driving in the city. So at 1.5 kilometers, we drove 75. At 2 kilometers, or 2 hours, we drove 100 kilometers. So 1.5 hours, 75 kilometers, 2 hours, 100 kilometers, 3, 150, and 4, 200. So it said graph against y equals x. Okay, well, let me get a graph board out. All right, so one thing when we're graphing data that's real life is we have to fit the data to the graph. Okay, so we see we have 200 here. Okay, well, I have about 12 or a little more than 12 right here. So somehow I had to figure that out. So I know I have at least 10 here. So 200 divided by 10 means that maybe each one of my verticals, maybe each one of my verticals should be 20. So if that's true, this is 40, this is 80. I've got my 100 right here. Can be really crowded if you write every one. So that's why I'm skipping. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So that's 200. Okay. So this is going to be distance. This is going to be distance and kilometers. Okay. So that's our y-axis. So sometimes we have to create the y-axis. Let's see. So this would be 140 and 180. Okay. So we have to be really good about creating our scale on the y-axis so we can represent our data. Now, time is always independent, so that means it's an output. We cannot change time. So we put time on this axis, which is the x-axis. And it's very, very infrequent that you would ever put time here because time is independent, which means it's an input. All right, so let's skip these. So let's every other one will be 1, 2, 3, and 4 since we have a half right there. Okay, so 1.5, we went 75 miles per hour. Okay, so that's going to be a bit of a guess because our scale. So we'll guess that one and we'll fix it with a line. So 2 hours.
Good morning, teachers. This is your monthly reminder to please check your daily symptoms check and also your absence tracking. Have a wonderful morning.
Okay, and then at 4 hours, we have 200 right here. Okay, so see how it all makes a nice linear line right there. So linear means line, so I'm like repeating myself on linear line. So then we can make a nice little line here to predict how we're going. And we use this so we can predict future events. All right, so let's see. It says graph against y equals x for 0. Oops, I should have carried this to 0. And I should have read the directions for 0 to 4. So it just wants to go right here. So that means we're going to stop there. So always remember to read the directions. Okay, we all forget to, so it's all right if we don't. Okay, and that's where we're going. So of course, if we're not driving, we're not going, or at time 0, we're not moving, we haven't gone any distance at all. All right, so find the slope of the graph and explain what it represents. Okay, so we want to find a rise and a run. So the best way to do this is looking at our data. We have 100 and 200. So let's rise, make a little slope triangle here and rise up to 200. So that's 100 for a rise, and our run here went from 2 to 4. So that's 2 hours. Okay, so we could say, okay, so our slope, which is the rise over the run, equals 100 kilometers. And if you use your units, it helps you understand what you're doing over hours. Okay, so that gives me 100 divided by 2 is 50 kilometers per hour. Okay, so that's how fast I am going to travel these distances. So I have to drive 50 kilometers per hour to make this kind of progress with distance over time. And then my next question is find the initial value of y. So that would be b, which is the initial value, the y-intercept. Well, look at that. It's actually 0. Okay, and then it says express y as a function. So, well, if we don't have a y-intercept, that's strange. So we're going to have 50 here, x plus 0, because we don't have a y-intercept that has a value other than 0. So that means that we're not going to write that 0. We're just going to write y equals 50x, and that's a direct variation. And it's a linear equation without a y-intercept. All right, let's go on to the next problem. Okay, so this one, we were given a graph. So we have a graph here, we have y and we have x. And y is water in a container in liters. So apparently we have, it starts at 12, and over time, 1, 2, 3, 4, 5 hours, it arrives at about 9. Okay, so it says, what is the rate and what does it show? Well, remember the rate is the rise over run. So if we rise from this, that means it's dropping -2 from here. Whoops, we're a little higher, -3. So be careful with your graph. So it's dropping -3, and it's running. That is running 5 hours. So in 5 hours, we're dropping -3 liters. All right. So we have the slope is going to be, and we've got to put the rise, which is the output, over the input. So the rise, let me write that out so you have that. So the rise is the output over the input. So we have -5. Oops, that's the, so we have to be careful. That's the x. This is the x value. So -3 over 5. So that means we're going to lose 3 liters in 5 hours. So if you can keep your units with your numbers, it really is helpful. So this is 5 hours and 3 liters. We've lost 3 liters in 5 hours. So that's what it's showing. What does 12 mean on the y-axis right here? Well, that's how much water we began with. Or, yes, how much water. We were using water. Okay, and how much water is there after 24 hours? Okay, so to do that, we need to predict this equation. So let's go and we have the slope, we have the y-intercept, so we can write an equation. Y equals -3 this x, and then we started with 12. So it wants us to find what happens in 24 hours. So we have 3/5, we put 24 in here because time is independent, so it's always the x, plus 12. Oh boy, that's not a nice equation. Okay, so we can't reduce, so that's a real bummer. So we have negative, let's see, 3 times 24, that's 12, 72 over 5 plus 12. So let's figure out what 72 over 5 is. So you divide, since 72 is in the denominator, we have 1, 5, 2, drop another 2 down, and we have 4 for 20. So we have 14 2/5. So we're subtracting 14 2/5 from 12. Well, does that make sense? We have y equals negative 14 2/5 plus 12. Well, it ran out of water at 12. Okay, so it's empty. It's beyond empty. It was empty a bit ago. Beyond empty. Okay, so it would have been empty at, if y was negative 12 plus 12, that is when it's empty. So if it's negative 14, well, we really don't need to calculate anymore. We know it's empty. Okay, so this is another example of linear modeling where we take a real life example and we put it into mathematics by creating linear equations. All right, you have a wonderful day. Bye-bye.